better. You can hear me now. I kind of reshuffled the order a little bit so that I can focus on the topics that are close to my heart. I'm a physicist, and I suspect that quite a lot of you, or many of you, are physicists. So I'm going to focus mostly on magnetic anisotropy, and the goal of the research that my own group does is trying to make molecules that are magnetic that you could actually use as bits of information or even bits of quantum information. I certainly won't get to the quantum information part, but there's a chance that I might get to the idea of using single molecules as magnetic memory elements. There are other examples that stretch into biology and chemistry, but it's very unlikely I'll get to that part of the talk. But if anybody's interested, you're welcome to contact me, come and see me while you're here, or contact me afterwards. There will be a tour of the labs tomorrow, around about the same time as there were tours today, so around 11 o'clock. So my talk's going to be more on the applications, so go through some of the physics of the interactions that we measure with EMR or EPR. I won't go into the technical details of how we do EPR. Hopefully you'll get some idea of that from the tour tomorrow. And you can also ask questions. So what is EMR and why high magnetic fields? EMR sort of encompasses a bunch of other acronyms that apply. Basically, it's anything to do with electrons in a magnetic field where you have some resonance phenomenon. So the standard one, standard terminology is either EPR for electron paramagnetic resonance or ESR for electron spin resonance, and I'll show you what I mean by that in a moment. But there are other forms of magnetic resonance, electromagnetic resonance as well. You heard the classic one this morning from Ryan Rogers, electron cyclotron resonance. There they trap chemicals and actually generate cyclotron motion of ions, but electrons in conducting systems also undergo cyclotron motion. And you can couple to that resonantly also and learn all kinds of things about the band structure of a material and so on and so forth. And we can do all of that as well, but I won't talk about that today. So with the same instrumentation that we use in my group, we can measure electron cyclotron resonance in metals, semiconductors. But I'm going to focus today on spin resonance or paramagnetic resonance. This is to give you some idea. Probably many of you know this, but I'll just go over it very quickly. You put a magnetic moment in a magnetic field, and rather like a precessing spinning top in a gravitational field, you know that it slowly precesses, and the precession frequency is related to the properties of the top and also the Earth's gravitational field. In this case, the torque on the magnetic moment is given by m cross b, and it generates this precessing motion with a Larmor frequency, which is given by its linear in magnetic field and inversely related to the mass of whatever the object is. In this case, so if it's an electron, you'll see in a moment. But if it was a proton, this frequency here, this Larmor frequency, is about 7.6 megahertz per Tesla. So if you put a 1 Tesla field on a proton, it will precess at about 7.6 megahertz. And this is the basis for nuclear magnetic resonance and magnetic resonance imaging, which you will recognize as an extremely powerful technique. Essentially, putting a magnetic field on and then flipping spins with radio frequency pulses. You can then, with clever pulse sequences, you can figure out how those spins relax back, and using gradients, you can actually generate images looking at how the protons in the water in a living object, how they relax, and that tells you something locally what's going on in the material. So it's an incredibly powerful technique with protons. And exactly the same thing happens with electrons. But of course, because the mass of an electron, which is in the denominator here, is about 2,000 times smaller, the frequency goes up into the microwaves. Instead of doing radio frequency pulses, you need microwave pulses in order to do electron spin resonance at 1 Tesla. That unfortunately has the effect that in that frequency range, water is extremely absorptive. So it's not a technique that's typically used in vivo imaging, because you just can't get microwaves to penetrate very deeply into human tissue. And as we all know, if you put something living into a microwave, it doesn't do very well. So, however, anything that has electrons, unpaired electrons in it, that's not particularly lossy, it doesn't dissipate a lot of energy. We can use electron spin resonance to measure what's going on. So of course, electrons are ubiquitous throughout the whole of science, from in chemistry, when chemical reactions are mediated by electrons hopping back and forth between different molecules. In physics, the whole of magnetism is due to electrons. Electronics due to motion of conducting systems that involves electrons. And even in biology, there is a vast array of things that happen in biology where you've got transfer of charges. And so it's a really nice technique for addressing a lot of those questions. So you get a electron in a magnetic field, processes at 28 gigahertz per Tesla. In a quantum mechanical picture, you can think of a spin half that can exist in two states, spin up or spin down, and you get a Zeeman splitting of those two levels in magnetic field, and the Zeeman splitting goes like h bar times 28 gigahertz per, well actually h times 28 gigahertz per Tesla. And so in a resonance experiment, what you're doing is you're shining microwaves on the sample with exactly an energy quantum that matches that difference, and then you get a resonant absorption when that energy difference matches the frequency of your radiation. So everything on the previous slide sort of was just for free electrons, but of course, if you're interested in some physics or chemistry or even biology, the electrons are doing something. So they're not just free electrons in vacuum. They interact with their environment. They reside in atomic orbitals that are involved in chemical bonding, and they therefore interact with, through those chemical through the orbitals that they live in. Those orbitals are oriented in such a way that they form chemical bonds with things nearby, and so those electrons actually know something about the environment in which they live. And if you're very clever theoretically, you measure an electron spin resonance or electron paramagnetic resonance spectrum, you find that you get shifts in the spectrum relative to what you'd expect if it was a completely free electron. And from the spectrum that you measure, you can learn something about the local environment. So you can learn something about the structure of a material. You can then learn something about the magnetism and so on. And spins also interact with each other through just either dipolar interactions or through quantum mechanical exchange interactions. They interact with nearby nuclei through hyperfine couplings and also through just dipolar interactions. And so through all of these couplings, you can really learn a lot about what an electron sees in its environment in a material. And that's a very, very powerful probe. So you can learn about structure. And if you know something about structure, or if you know something about the Hamiltonian describing the electrons in the system, that can tell you something about the magnetism as well. So it's a really important tool in physics. So as I've hopefully impressed upon you by now, it's a technique that spans all the way from physics through to chemistry and through to biology. So the users of our facility, they're about 50-50 between physics and chemistry and biology. So I lump chemistry and biology together into one. So we get about 50% of our users work on material science and physics, and about the other 50 are interested in chemistry and biology. The user support staff in the group are also qualified in these various different areas. So we have, I'm a physicist, we have 2 chemists user support, we have a physics user support, and a biophysicist as well. This is really the only technical slide that I have in the whole presentation. You'll learn more about this when you do the tour. But the basic idea is that you have some source of microwaves that you shine down into a sample, and then you either transmit that microwave through the sample or you look in reflection. So then you have some detector. And if you're very clever about the way that you do things, you can use some frequency modulation and a phase-sensitive detection to get very, very high sensitivity. Again, I don't want to go too much into the technical details of how we do this today, but there are obviously a lot of tricks that one can play to really improve the signal to noise. But if in a typical experiment, what we do is we shine a fixed frequency onto the sample. If it was a free electron and we've shone 28 gigahertz onto the sample, at 1 Tesla, the Zeeman splitting for the free electron would be exactly 28 gigahertz. And so we would see some absorption right when our Zeeman splitting matches the frequency of our photons. And of course, the line shape contains a lot of information as well. It's related ultimately to the lifetime of the excited state, but If you're looking at an ensemble, the line width can tell you something about the distribution of environments that the electrons reside in. If you're doing field modulation, what you actually end up very often is measuring a derivative. I just point that out here because there are a few spectra that in my presentation where the resonance is represented as a derivative rather than absorption. So the absorption would obviously look like a Lorentzian or a Gaussian, but if you apply field modulation and then detect in phase with the field modulation, you get something that looks like the derivative of the absorption. So here at the Magnet Lab, we can, the magnet in this scheme here can be any kind of magnet, electromagnet. A lot of commercial EPR is done just using a regular electromagnet, water-cooled, that provides fields of up to about half a Tesla or so. No superconducting magnet or anything like that. You can just do this via normal electromagnets. But we employ a whole range of different magnets here at the lab to do EPR. In our own labs, we use superconducting magnets that go up to at least, up to about 17 Tesla. But all of our, not everything, but nearly all of our instrumentation can actually be ported over to the 45 Tesla hybrid magnet. So we can essentially cover the entire field range that's available here at the lab in Tallahassee. If you then take that 28 gigahertz per Tesla paradigm, that's this dashed line here. So you can see that if I'm going to go up to about 35 Tesla, which is around about the highest field resistive, purely resistive magnets, then if I was to look at electrons that are free, very weakly interacting, I need 1 terahertz in frequency in order to do my ESR measurement. Turns out that this range here from sort of about 50 gigahertz up to a terahertz and even up to 2 or 3 terahertz is a very, very difficult range to do spectroscopy in. And in fact, we're more limited along this axis in what we're able to achieve at the lab than we are along this axis. Of course, the DC facility provides 45 Tesla for us, more or less when we have to apply for the time, but it's always there when we want it. But our ability to do ESR as we go to higher and higher frequencies gets more and more challenging. And the reason is the technology is just not there. Our cell phones work at about up to about 10 gigahertz or so. And really there isn't a whole lot of technology that occurs beyond that until you get up into the infrared. So there's this well-known terahertz gap where it's very challenging to produce high-power electromagnetic signals in that range. The only sources that we know about currently that are very powerful and bright are sort of multi-million-dollar synchrotron type sources. So the way that we do it, just very briefly, is we start with a low-frequency oscillator and we multiply up using nonlinear devices. And so we multiply up. We send the frequency that we want to our experiment, and then we mix it back down with a reference and detect again in the sort of 10 gigahertz range or so. So we play a trick of multiplying up and then mixing back down to a low frequency to do these measurements. So this shows you the sort of frequency that we would need if we were talking about purely free electrons. But of course, in a real material of the system that we're interested in studying, in addition to the Zeeman interaction for the free electron, there's a lot of microscopic physics. And it turns out that when you start to plug in that microscopic physics that I'm going to talk about next, the excitations don't really lie on these lines. It gets driven off very far from this line. So in fact, of the materials that we're interested in the Magnet Lab, we really want to be able to do experiments over this entire two-dimensional space. So anyway, there could be experiments where we're doing very low frequencies but at very high fields, or in some cases there are experiments where we're at very high frequencies but at relatively low fields. Obviously, you don't necessarily need the Magnet Lab to do the experiments here because you're talking about fields of just a few Tesla, but we're one of the few groups in the world that have developed the expertise to do the experiments here. So it's still a unique capability that we have here, and there really aren't many other groups around the world that can do experiments in this region here. So we sort of pride ourselves on covering this entire space. Commercial EPR spectrometers are limited to this little blue box down here, and even the one here that goes up to about 95 gigahertz is about $1 million spectrometer, or even a little bit more. Your average spectrometer works at 9 gigahertz, which would barely fill a space the size of my little fingernail down at the bottom corner here. So most EPR using commercial instruments is done at about 9 gigahertz and about 0.3 Tesla. And so you can see that we're covering a range that's really quite massive compared to the commercial instruments. There is one or two commercial instruments that have very recently been built up here, but they're multi-million-dollar prototype instruments that are not easily purchased right at the moment. And then we cover this entire range where we just do pure spectroscopy, where we just look at the absorption as a function of magnetic field, but we can also do pulsed EPR experiments, time domain experiments, where we send pulses and look at how spins relax. That's a even more challenging experiment to do because in a pulsed experiment, you need to have a lot of energies in the pulses so that in a short amount of time you can flip your spins at least 90 degrees. So you need very, very high power microwave sources in order to do pulsed experiments. And these yellow dots represent regions where we can do pulsed EPR. And this instrument here is unique. There's nothing anywhere else in the world. Nobody can do pulsed EPR at these high frequencies of 336 gigahertz, which is our record. So I'm going to talk often about gigahertz. 30 gigahertz, which, as I've told you, is roughly about 1 Tesla, because it's 28 gigahertz per Tesla, is the equivalent of 1 inverse centimeter, or about 0.12 millivolts. So 1 Tesla is about 0.1 millivolt, for those of you who are used to millivolt units, or about 1.5 Kelvin or so. So why am I interested in high field EPR? It's now really narrowing down the applications a little bit, but I will come back and give you some other applications as I go on. You know, this figure, everyone's seen this sort of Moore's law type picture where you look at the areal density of magnetic storage devices versus year, and as you won't have escaped you that every time you buy a new computer, the hard drive capacity goes up, or the size of your device goes down. So you know, if you keep on extrapolating this Moore's law out into the future, you know, eventually you get down to the size of fundamental particles. I mean, atoms, molecules, probably never down to things that are spaced the size of a nucleus. But although one could store information in a nucleus, so at the moment, you know, we're sort of somewhere around about here. And we're starting to run into these fundamental limits. So Moore's law is starting to break down. So there has to be a big paradigm shift in the way that we write information in order to keep this trend going up. And sort of everything up until now is based on a top-down approach, where you're just basically shrinking, continually shrinking the size of the area on your device to make it smaller and smaller and smaller. So you can imagine you've just got some magnetic grain of magnetic material, and you're making that grain smaller and smaller and smaller. But my interest, and an interest of many of our users, is coming from the other side and starting with chemistry and building up from the bottom up. So starting with, you know, maybe one day we can write to individual atoms, but let's see if we can build magnetic particles from the bottom up. And the nice thing about chemistry is it can give you very reproducible objects like this nice manganese 12 cluster here. That behaves like a magnetic object, and maybe it's magnetizable. You can actually use it as a bit of information. And so if you do that, you've got the potential for you know, keeping on this curve towards hundreds or even thousands of terabits per square inch. The chemistry allows you to functionalize them so they form nice arrays on surfaces, and every molecule is in principle identical, which is important when you get down to the small scale, because quantum effects start to play an important role when you get down to the atomic scale. And quantum mechanics is extremely fussy about things like parity. So if you have an even or an odd number of electrons on your magnetic dot, it can behave completely differently. So you need your objects to be very reproducible, and you need to be able to understand the quantum mechanics if you're going to do this bottom-up approach. But you also need very, very strong magnetic anisotropy, because it's magnetic anisotropy that's the origin of magnetic bistability and the reason why a magnetic memory stays up or down. So the idea is, of course, if you've got a magnetic particle, it's in, say, some up state, it should have, in the absence of an applied field, the up and down state should be equally, have the same energy, so they're equally lightly. But you want some kind of barrier between that prevents the downspin flipping over and becoming an upspin. So it's that anisotropy barrier. So if you like here, this is the energy versus the orientation of the magnetic moment. You want that barrier to be large compared to kT, so that if your memory is going to be long-lived. And when you have a large magnetic, it turns out this anisotropy is a thermodynamic quantity, extensive quantity. It basically scales with the size of the object. So that's why we're running into these fundamental limitations now, because as you shrink magnetic objects smaller and smaller, the magnetic anisotropy associated with the object gets less and less and less. So this barrier comes down, and eventually you hit what's called the superparamagnetic limit, and at room temperature the objects can just fluctuate thermally due to the fact that this barrier is only 300 Kelvin. And so if you're going to make things smaller, you need to find ways to make this barrier bigger, or you would have to operate your memory at a lower temperature, which is not a completely crazy idea, but probably not in everyday applications. But as I mentioned, the other problem is quantum fluctuations that can cause a problem as well. This classical picture here, as you shrink and quantum effects start to become important, there can be other ways you can short-circuit this barrier through quantum tunneling, essentially. And that's something that we've been very interested in when studying these kinds of objects. So I'm going to spend a little while now talking about magnetic anisotropy. What are the origins of magnetic anisotropy? Because they play a role not just in trying to make magnetic memories, but they can play a role in the phase diagram of your favorite quantum spin system, if that's where where your interest lies. And magnetic anisotropy ultimately influences an EPR spectrum, and from the EPR spectrum you can learn something about the structure of the material that's basically related to its anisotropy. So there's kind of this feedback loop. Structure and anisotropy are related to one another. So if you understand the magnetic anisotropy, you can use EPR to understand the structure of the material. So there are two interactions that are important. There's the spin-orbit coupling. So if there were no spin-orbit coupling, an electron would live in an atomic orbital, and it would know nothing about the orbital, right? It would just be a spin sitting there, and you would be coupling in an EPR experiment to the spin alone. But through the spin-orbit interaction, the spin knows that it lives in an orbit that has a certain orbital angular momentum associated with it. But the other important interaction in materials is the crystal field. So I don't know whether I mentioned that here. I'll come to it in a moment. Oh yeah, here it is, the crystal field interaction. So if you have an electron in an atom, it has to couple to the orbital angular momentum in order for the spin to know something about the orbits that it lives in. But then that atom makes chemical bonds with neighboring atoms. And so they provide, if you like, a very naive picture. You can think about it as a crystalline electric field. And so the electric field produced by neighboring atoms in the material has an effect on the orbitals that associated with the atom in which the electron lives in. And that's you need both of these to give rise to magnetic anisotropy. Because if you have no crystal field, the atom is just free to rotate. There's no anisotropy. If the atom is locked in by the crystal field, but there's no spin-orbit interaction, then the electron's free to, it's totally spherically symmetric. So when you put these two things together, you get the magnetic anisotropy associated with the electron itself. And it's the interplay between these two interactions that's going to be very important. So I actually start way down in the periodic table with the lanthanides, because I kind of think that they're easier to understand. In the lanthanides, so the spin-orbit interaction is a relativistic interaction. So it depends, if you like, on the velocity of the electrons in their orbits. And so as you go further down the periodic table and the nuclear charge gets larger and larger, relativistic effects become more and more important. So as you go down the periodic table, spin-orbit coupling gets stronger and stronger and stronger. And so in the lanthanides, it's the spin-orbit interaction that's the dominant energy scale of, order of thousands of wave numbers or thousands of Kelvin or hundreds of MeV, milli-electron volts. On the other hand, with the lanthanides, the important electrons in lanthanides, the magnetic electrons, live in contracted orbitals, the F shell, which is very contracted compared to the shells that do the chemical bonding. So it turns out that the F electrons in lanthanides don't couple very strongly to the surrounding atoms. So they don't couple very strongly to that crystalline electric field. It's screened out by the S and P and D shells that extend beyond the F shell. So the crystal field is weak and the spin-orbit coupling is strong. So as you go through a scheme where you treat each interaction and then the subsequent interactions as a perturbation, you start with the spin-orbit coupling, and it has the effect that the spin and the orbital angular momentum and the spin, they couple very strongly to one another to give you a total angular momentum that we label J. So if I start with cerium, which has one electron in the F shell, it has a spin, because it's just one electron, there's a spin of a half, but it goes into the orbital with the largest contribution to the orbital angular momentum first. So you have an L of 3 and a spin of 1/2. And it turns out that when you're less than half filled, the total angular momentum is actually the difference between those two numbers. So you end up with a J of 5 halves. So the orbital angular momentum of, so the total angular momentum of cerium would be J of 5 halves. And it resides in this particular orbital here, which is rather oblate. So if you look at the electron density associated, it's not spherical. It looks like a squashed sphere. Now, if you go on filling, I'm not going to do each one because it would take me too long. But so we put in 3 electrons. Now we have 3 halves of electron spin. They go in parallel according to Hund's rule. That ensures that they won't, by putting them in parallel, that Hund's rule prevents them going into the same orbital. So you get an energy saving by putting them in parallel. You get 3 halves spin. And now you put the first electron in the L equal 3, the second one in the ML equal plus or minus 2, and the third one in the ML equal plus 1. So you get 3 plus 2 plus 1, so you get an L of 6. And again, they go in anti-parallel, so you get a J of 9 halves. But now you've got electrons in 3 different orbitals. This one's rather oblate, and this one's stretched more along the Z direction. I'm going to show you in a moment what the sum of those electron densities looks like, but it's more spherical than the case when it just goes in with 1. And you can go on. Here we got 6 electrons, so you've got a S of 3 and you've got an L of 3. So europium's kind of interesting. It's got all these electrons, but it actually has no moment because they go in opposite to one another, so it's non-magnetic. And then gadolinium's a nice example because you completely fill the F shell. You get an S of 7 halves, and the J is entirely due to the spin. And then you can go on filling again, but you put the spins in the other way now. So holmium has a spin of 2 because these are all paired, these are not. And you have an L of 6, 3 plus 2 plus 1 plus 0. And now when you're more than half filled, they go in parallel, so you get a J of 8. So you get a really large magnetic moment. So holmium would be something really nice if you could make magnetic memory out of this. And there's certainly many efforts worldwide now to try to do that. So if you sum the electron densities for all of these different lanthanides, and this applies quite well for just about any material you look at. Because these F shells are so contracted, it really doesn't matter whether you're looking at a heavy fermion material or if you're looking at a molecular magnet or whatever. The electron density with terbium is basically a squashed sphere, whereas the electron density of ytterbium is more like a stretched cigar shape. So depending on which orbitals you fill, you get these rather odd-shaped electronic densities associated with the different lanthanides. Gadolinium, because it fills all of them, it's nice and spherical. Now you imagine you attach something on the outside of your lanthanide, you put some charges in a very clever way. You can see that if you take, for example, terbium, if I put charges above and below, the terbium's quite happy with the sphere. You imagine it's a squashed sphere. It's quite happy, or it's like an M&M, for example. It's quite happy when the plane of the M&M is horizontal, but it doesn't like it when it's turned on its side because the lobes of the sphere then point towards these charges. So now this is how you go about making a magnetic memory. So you have a much higher energy so you have the lowest energy when the spin is up and down, and the orbital state is flat, and you have a higher energy when it's in this configuration here. Or alternatively, one of these guys, you could put the charges around the equator, and you end up with the same thing. So chemists figure this out, and they start to realize we can make interesting looking molecules. So this example is for example, a lanthanide trap between two phthalocyanine ligands. So these sort of provide a ring of charges above and a ring of charges below, so it's very much like this situation here. And so if you put terbium in between here, you end up with exactly what you want. You end up with, so terbium is J equals 6. You end up with J equal plus or minus 6 as your ground state, and then a big energy barrier preventing reorientation of that barrier. And chemists have now succeeded actually in making molecules that are bistable in exactly this way. The only problem is the temperature is still quite low. You have to go below about 16 Kelvin or so to see this bistability. In a quantum mechanical picture, this shows just the shapes of all of the different M sub S states of these different orbitals for 6 of the lanthanides. And so now you've got a sort of discrete energy spectrum. This is for terbium, minus 6, plus 6, and all the states in between. So it's not a nice smooth barrier. There's sort of a little minimum up here, but you can see you have exactly what you want. You have about 450 wave numbers separating the lowest state and the barrier. And now, in principle, in an EPR experiment, we could try to measure these transitions between these different M sub S states. So that's the lanthanides, where L is strongly coupled to S. So the J ground, the energy scale that locks L onto S is thousands of wave numbers, and it's the crystal field that's of order of a few hundred wave numbers. But when you go to transition metals, you have the opposite. So in transition metals, the d electrons are actually responsible for the bonding. So they interact very strongly with the surrounding atoms in which that form the chemical bonds. And so in this case, it's completely back to front. So you have crystal field energies now that are often thousands of wave numbers. And the electrostatic picture that I've shown you up to now is is a bit of an oversimplification, because you have to worry about covalency and so on, and a lot of quantum mechanical corrections. But still, you get crystal field energies that are often thousands of wave numbers. But the spin-orbit coupling is much weaker because you're much higher up the periodic table, so relativistic effects are weaker. So now it's the crystal field energy scale that you have to treat first, and then you treat the spin-orbit coupling subsequently. So for example, if you look at the D shell here are the 5 d orbitals, dz squared, dx squared minus y squared, and then dx, dxy, dxz, dyz. If we now form an octahedral complex, which is quite common for d elements, so you can think of a minus charge at the vertices of each of this octahedron. The lobes of the dz squared point along those charges, and so do the lobes of the dx squared minus y squared. So as a result, the energies of those two orbitals are higher in energy, because you've got electrons in here pointing directly towards the minus charges, whereas the ones that have their lobes pointing between those vertices, they lie lower in energy. So for a perfect octahedron, you end up lifting a lot of the orbital degeneracy. And so you have what we call 2 EG states here that correspond to these two orbitals, separated from the 3 T2G states that correspond to these 3 orbitals. And that splitting can be many hundreds or thousands of wave numbers, depending on the system. You still have a degeneracy here. So this example I'm using here is actually copper, which is 3d9. So all of the orbitals are occupied except for one, which is half occupied. So if it was perfectly octahedral, you still have some orbital degeneracy here. And nature doesn't like degeneracy, so it will typically distort, something called the Yandel distortion. So the molecule distorts, or the atom, whatever it is, it could be a lattice or it could be a molecule. The lattice distorts, or the molecule distorts in such a way that it lowers the energy of the state that has the 2 electrons in, and it saves energy that way. And now you have just 1 electron left over in this dx squared minus y squared orbital, so the one that sits in the plane of the distorted octahedron. And that's where the magnetism is going to come from, because all of these electrons here are paired. So that's the crystal field splitting. Now you have to put in the spin-orbit coupling in order for that spin to know something about its anisotropic surrounding. And this, of course, now is a perturbation. And so you have an interaction, the spin-orbit interaction enters through sort of this perturbative term here, So it enters through the way that the different angular L operators mix this state with the other orbital states. It turns out that you can't mix x squared minus y squared with dz squared because they correspond, if you like, to the ml equals 0 and ml equal 2. But you can mix it with these two states here. And so you end up with then a renormalized Zeeman interaction. So instead of having just G mu B times S, you end up now with a Zeeman interaction that has instead of a G factor, it has a G tensor. And that G tensor contains the information about how this state mixes with the other orbital states. And so again, it can be related back to the structure of the system. And so by measuring the different components of the G tensor, we can actually then measure the different components of this perturbative term, and then we can know how the different L states mix, and then we can piece together what the local structure must have been in order to produce that particular G tensor. And then also that G anisotropy may also have important effects ultimately on the magnetism of the material. So by a G tensor, what it means is now, and maybe this is demonstrated in the next few slides. So if you have a free electron with just a G factor of 2, I put a magnetic field on and I get 28 gigahertz per Tesla, no matter where I apply the magnetic field. But if I now have a material which has undergone this kind of Yandel distortion here, it makes a difference if I put the magnetic field along the direction of the Yandel distortion or perpendicular to the Yandel distortion. So my EPR spectrum, as a function of field orientation, tells me something about the local symmetry, about the site which contains the magnetic electron. So, now we parameterize this all in terms of this G factor, which for a free electron is roughly 2. So when you have a G factor of 2, you have a Zeeman splitting of exactly 28 gigahertz per Tesla. But if it's slightly more than 2, then it would be a little bit more than 28 gigahertz per Tesla. And you can see for copper, in this Yandel distorted copper here, you have quite a large anisotropy in the G factor. It varies from about 2.06 in this particular material. It differs from one material to another, but very often for copper in a Yandel elongated situation, it varies from about 2.06 to about 2.3. So now when I look at my EPR spectrum as a function of the orientation of the field relative to the c-axis, where the c-axis is the direction along which the Yandel occurs, I see that my spectrum moves. It oscillates with position. So, just to give you an application, a nice, fun application of this, this is an example of a copper coordination polymer. So again, it's copper, so it's exactly the same situation I showed you on the previous slide. The copper sits here along in this chain linked by pyrazine molecules. So these are carbons with nitrogens in 2 positions here, and then hydrogen and hydrogen. So you've got copper, nitrogen, nitrogen, copper, nitrogen, nitrogen, copper. And then in the plane, you have a couple of oxygens that are associated with waters, and then you have fluorines. And at ambient pressure, the Yandel elongation is actually along these copper-nitrogen bonds. So this bond along the a-axis is actually longer than the bonds in the plane here. That means that the electron, the magnetic electron resides, if you go back to this picture, remember, the electron resides in the x squared minus y squared orbital, which is this one. So it resides in this plane. It turns out, so this is just one chain, but in the crystal of this material, there are many of these chains that just form a 3-dimensional network. And there's fairly good magnetic communication because the electron lives in this plane, where this gray plane is here. There's pretty good communication between the electron in this copper and the one on the next chain and the next chain and so on. But there's very poor communication along the chain because there's no electron density along the dz squared orbital. So you end up with a 2-dimensional network, and so you end up with a 2-dimensional quantum antiferromagnet in this particular material. It undergoes it actually orders at a few Kelvin, but it's a nice model system for studying 2-dimensional magnetism. But if you apply pressure, so this picture here shows you the measure of the G factor. So we've taken this particular compound, put it in a magnet where we can put the field in any orientation that we want. In fact, it was Rick who's going to talk to you at lunch that sold me that magnet. It's a vector magnet which allows you to power 3 orthogonal coils in any direction. And so we can measure the G factor over the complete sphere. And you can see this is the high value of the G along the A-axis, so it's along the axial direction. And then you have a low value of the G in the plane, in this plane where the electron resides. And when you squeeze the thing, it undergoes a phase transition where instead of the Yandel being along the nitrogens, all of a sudden it flips and it's along the oxygens. And we can see this then in the symmetry of the G tensor. And when that happens now, you've shoved the electron density, instead of being in this BC plane, it's now in the AB plane. And so now you've got good communication along these chains. And it turns out, and I don't have a good picture to explain why, but it turns out you switch interactions along the chain, you switch them on, but you switch off the 2-dimensional interactions within the plane. And so you go from a 2-dimensional quantum antiferromagnet to a 1-dimensional quantum antiferromagnet at these pressures. And you can really see that directly in the EPR experiment, how the electron density flips from being in the plane containing the oxygens and the fluorines to being in the plane containing the fluorines and the nitrogens. So why would we need high magnetic fields? This is an example of an EPR spectrum obtained from a powder. So this is a very quick way that allows you to measure all 3 components of the G tensor. So if you take a powder of a sample, you crush it and get really totally random orientations. Now you sweep your magnetic field and you'll start to see an onset of absorption at the largest value of the G tensor. And then you'll stop seeing absorption when you get to the lowest value of the G tensor. If you take a derivative of that spectrum, I think you can all agree it's quite, you're going to get a peak where you start to have onset absorption, and you're going to get a dip where you see the absorption turn off. And so those two, the peak and the dip, will tell you what the maximum and the minimum G values are in one single measurement. But it turns out you also get the Y component as well. You also get the intermediate value as well. In the same way that a X-ray crystal structure of a powder gives you all components of the scattering, the same happens in an EPR spectrum. So this is an example of an axial system where you've got one G factor that's very well split off from the other 2, but a very small difference between the 2 G factors here. This experiment is done at 9 gigahertz, so a very, very small magnetic field of about 0.33 Tesla or so. It's very hard to see the difference between these 2 components. But as we go to higher and higher magnetic fields on exactly the same compound, I've gone to higher magnetic fields. I've gone to 33 gigahertz here. This is actually a simulation. It's not a real measurement. So I've only multiplied the frequency by 3, but I kept the magnitude of the horizontal scale to be exactly the same. So it's 0.2 Tesla across the bottom. So here it's 1.05 to 1.25, so the same horizontal field range. You can see that the splitting between those 2 components is much more easily resolved when you go to the higher frequency of 33 gigahertz. So the point is your resolving power, your ability to resolve different components of the G tensor improves as you go to higher magnetic fields. And here's an example of where we're looking at the G tensor of a carbon-based radical. It's actually a tryptophan that lives on some biological molecule here. And because it's living on a carbon-based system, carbon is one of the lightest elements that it's not the lightest, but it's one of the lightest elements which things are made up from. There's virtually no spin-orbit coupling because it's a very, very light element. So the relativistic effects are almost negligible. And so there's very, 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 very weak splitting in the G tensor. And this measurement was done up at about 25 Tesla and a frequency of about 700 gigahertz. And so you had to go, if you try to do this experiment even at 100 gigahertz, you couldn't resolve these 2 components of the G tensor here. But even better than that, what you find is when you prepare this azurin protein in 2 different forms, you can actually measure a difference, a very, very small difference of about 75 parts per million in the G tensor. And then using quantum chemical calculations, you can actually infer. So this is actually putting theory and experiment together. You wouldn't just look at the experiment and immediately infer this. You have to do a lot of high-level theory. You have to have some hypothesis to begin with. but you can actually infer that there was a hydrogen bond between this nitrogen and the backbone of the azurin protein in one case, and that bond was not present in the other case. And it's sort of a very simple way to see this. When you form this hydrogen bond, the electron becomes even more delocalized, so it behaves more and more like a free electron, so its G-tensor becomes even less anisotropic, it's even less spread. When the hydrogen bond goes away, the G-tensor spreads out because you're essentially localizing that electron on the organic molecule. So almost like the uncertainty principle, by localizing it in space, its anisotropy becomes larger. So these are real heroic experiments that could only ever be done at the magnet lab. In the interest of time, like I said, I've got quite a bit more, but I'm going to stop here. I didn't show you examples of us measuring highly anisotropic transition metals with the idea of making molecular magnets, but hopefully I've given you some idea that using EPR, you have this access to measuring magnetic anisotropy, and that's an important ingredient for a lot of the things that people are interested in here at the Magnet Lab, and I'm happy to take any questions. I have one up here.
So, excuse me. Already you made the spin orbit coupling and magnetic anisotropy. So, have you ever tried measuring any of the chiral magnets or the system that doesn't have inversion symmetry?
So that's a very, very good question. So we've published quite a lot of work on. So I haven't directly studied chiral systems, but we have been very interested in looking at terms in the anisotropy that break inversion symmetry. Yes. So everything I talked about here was on-site anisotropy. So spin orbit coupling correction to the, say, crystal field anisotropy. And it turns out the nature of those interactions necessarily preserve they preserve time reversal invariance, and they don't give you terms that break inversion symmetry. However, when you do spin-spin interactions, you can get terms can arise way more complicated than the ones that I've shown here that break time reversal invariance. So the famous Jalashinsky-Morier interaction that will give you can give you these staggered moments and spiral. And there's a lot of our users are interested in that, have published papers on this topic. So if you go to the EMR website and look that up, you'll find several papers on frustrated spin systems. But also, we've done quite a bit of work ourselves on organic ferromagnets, where they don't have interesting magnetic states, but it turns out we were able to get a lot of fundamental insight into these anisotropic terms from a very fundamental level.
So is there any moment strength limitation? That several chiral magnets, they have really high magnetic moment, couple of Bohr magneton, but some of them have really, really small moment, let's say a few percent of a Bohr magneton, and you can see the neutron experiment. That's impossible. But since this is in EMR or APR, it might be susceptible to that. So if it's doable, I can actually apply for some time here.
Yeah, it's a very good question, because EMR and neutrons are obviously highly complementary techniques. Neutrons got some disadvantages, that you often need large samples, you need stuff which doesn't have a lot of protons and things like that, and that good large single crystals. There are certainly cases where you can gain the same information from EMR. You have to be a little careful, because the selection rules for EPR are different from the selection rules for neutrons. So neutron measures some things better than electron EMR does. However, there are definitely cases where we can measure these anisotropic terms in EMR. I'd have to know the specific case more directly, but we're often worried about that. What can we do that neutrons can't, or what can we do much more easily, or with a smaller crystal? Because we don't need much sample. We can get away with really, really tiny crystals. Yeah, and it's relatively low cost, especially if you don't use the resistive magnets. If we do it in our lab with a superconducting magnet, it's a very low cost experiment.